All right, so chapter 16, kind of a long chapter, but some of this stuff is going to be reviewed. So back in chapter 4, we spent a section and a half on acids and bases. One, just talking about the definitions of acids and bases, how to write out acid-base neutralization reactions. And then we did a little bit of an acid-base titration just to determine either the concentration of an unknown acid or base, or to determine the volume of a titrant needed to complete a neutralization reaction. So that was from chapter 4. So we're going to start off by talking back about the definitions of Brønsted acids and bases, how we recognize what's an acid and a base, how we write those equations, and then we'll go into the acid-base properties of water and bringing in the equilibrium that we learned from chapter 15 to introduce the idea of the pH scale, which I know we went through an entire semester of chemistry without ever mentioning pH, but we're finally going to talk about pH because pH is based on equilibrium, so we had to do equilibrium first before we could talk about pH. And then we'll talk all about the weak acids versus strong acids. We talked about them briefly in chapter 4, but not really what the big quantitative difference is between them. Now we'll look at that, and we'll talk about strength and beginning to talk about the acid-base properties of salt solutions, how things can act as an acid or a base when they are a salt, and then the Lewis acid definition. And then in chapter 17 is when we will do all of the acid-base titration problems. So it looks like a lot, but some of these sections are kind of short. So first of all, in chapter 4, we introduced the Arrhenius definition of an acid or base. Actually, I think we introduced that back in chapter 2 when we first defined an acid or base for nomenclature reasons. And we defined it by the Arrhenius definition as just something, an acid is something that releases hydrogen plus ions in solution, and a base is something that releases hydroxide minus ions in solution. And that was a very limiting definition. There were a lot of things that we know are acids and bases that weren't covered by that. So in chapter 4, we introduced the Brønsted-Lowry definition of an acid and base. And in this case, we have to look at how it reacts in an equation rather than just looking at the formula to determine if it's an acid or a base. So in the Brønsted-Lowry definition, an acid is a proton donor. Well, when we mean proton, we mean the H plus ion. And a Brønsted base is a proton acceptor. So in any reaction, there's going to be something acting as an acid that donated its proton, something acting as a base that accepted that proton. So we can also have water acting as our acid or our base. So in this case here, we've got HCl. We know that's an acid, but when we act it with water, the hydrogen ion is donated by the acid to the H2O, which is acting as our base, turning H2O into hydronium, H3O+, and turning the hydrochloric acid into just the chloride ion. So terminology we didn't use last time was the idea of a conjugate acid versus a conjugate base. Once an acid has donated its proton, so in this case HCl is our acid, once it has donated its proton, what is left over is called the conjugate base. So the conjugate base is what is left over after an acid has donated its proton. Likewise with a base, so here we have ammonia acting as a base, so that means it's going to accept a proton. In this case, it's going to accept one of the hydrogens from the water and turn ammonia NH3 into ammonium NH4. So the conjugate acid is what is left over once a base has accepted a proton. So in an acid-base reaction, an acid will turn into its conjugate base, and a base will turn into its conjugate acid. So if I just give you the formula and ask you what is the conjugate acid or conjugate base, all you're going to do is add or remove one hydrogen, just one at a time, one hydrogen at a time. So if I have an acid and I want to know its conjugate base, am I adding a hydrogen or removing a hydrogen? If I'm starting with an acid, is it going to lose a hydrogen or gain a hydrogen? Lose a hydrogen. So if I give you an acid and ask you what's the conjugate base, just remove one hydrogen. So this first one I have up here, CH3COOH, that is acetic acid. It's a form we haven't really seen it very often in. In Chapter 2, we introduced acetic acid as just the acidic form of the acetate ion, and we wrote the acetate ion as C2H3O2 minus as the acetate ion. And then when we added a hydrogen, we usually would just add it in the front. That was how we wrote the acetic acid back in Chapter 2. But here we have it written out in the form that the molecules actually spread out in. So this molecule is actually spread out, a carbon bonded to 3 hydrogens, then bonded to a carbon, bonded to 2 oxygens, and one of those oxygens has a hydrogen. So although these look different, they are actually the same. They're actually the exact same molecule. It's just a different way of writing it. Now, in the way of writing it, this hydrogen on the end here is my acidic hydrogen. That's the proton that's going to be lost in an acid-base reaction. These hydrogens here are part of our acetate ion. They are not going to be lost. They're going to be inside of the polyatomic ion, so they are not involved in the acid-base reaction. The other ones are a little bit more obvious. H2O loses a hydrogen, it becomes hydroxide. We've seen that one. Ammonia. Now, we haven't really talked about ammonia acting as an acid. We always talk about acting as a base because it's so easy to add another hydrogen onto ammonia and make ammonium. But it has 3 hydrogens, so technically it can act as an acid. It can donate one of those hydrogens and become NH2 with a negative charge and act as an acid. H2SO4, what is this? Good, sulfuric acid. To become its conjugate base, why did it not become sulfate, SO4, 2 minus? Why is the conjugate base of sulfuric acid not SO4, 2 minus, sulfate? Why is it not sulfate? In Chapter 4, we were learning about acid-base reactions and talking about moving around a hydrogen. What was the rule about how many hydrogens we could move at a time? Just 1. You can only remove 1 hydrogen at a time. So the conjugate base of sulfuric acid is not sulfate, it is hydrogen sulfate, because we can only remove 1 of these hydrogens at a time. Hydrogen sulfate can then have a conjugate base of sulfate. But as we learned in Chapter 4, you lose only 1 hydrogen in each step. So from any acid or anything that can act as an acid to find its conjugate base, just remove 1 hydrogen. And make sure it's not a hydrogen inside of a polyatomic ion. Likewise, to form a conjugate acid, we're going to do the opposite. So instead of removing hydrogen, we're going to add a hydrogen. So ammonia, we already saw, its conjugate acid would be ammonium, NH4+. Water, we already saw, its conjugate acid would be hydronium, H3O+. Hydroxide, acting as an acid, add 1 more hydrogen, we've got water. We saw that in the acid-base neutralization reactions when we were writing out the net ionic reaction of a strong acid, strong base neutralization. We saw the hydroxide gains a hydrogen and becomes H2O. Down here is urea, H2NCONH2. Now, back in Chapter 4, when we were first learning about the properties of solutions, one of the properties we talked about at the very beginning was whether or not something was an electrolyte. And the most confusing part about that, I think, for students was determining whether or not something was a molecular base. Anybody remember what I said was the giveaway for whether or not something was going to be a molecular base back in Chapter 4? It ended with what kind of a group? An amine group. Good. So an amine group is an NH group. So looking at this NH group means by our definitions back in the Chapter 4, this is a molecular base. Now, as we can see here, not everything here is an amine group, but it could still act as a base. But that means it's a very good base if it's going to end with an amine group. So that amine group is going to act just like ammonia adds another hydrogen. The amine group is where we're going to add another hydrogen to when this acts as a base. And both of these tables are on page 720 if you're following along in the book. So identifying in the reaction. In chapter 4, we identify what was the acid and the base. Now we're going to go one step further and say not just what's the acid, but what is its conjugate base, what is the base, and what is its conjugate acid. So the acid donates the hydrogen. Its conjugate base is what is left over once it has donated its hydrogen. The base is what accepts that proton. Its conjugate acid is what is left over after it has accepted. So on our reactant side, we're going to have an acid and a base. On our product side, we're going to have a conjugate acid and a conjugate base. And we can have the same thing for a base, like ammonia here. Our base turns into a conjugate acid. Our acid turns into a conjugate base. So let's try out some examples. First of all, just determining what is the conjugate acid conjugate base. So we're just adding hydrogens and removing hydrogens here. So first question, what is the conjugate base of HNO3? So if I'm asking for the conjugate base, am I adding a hydrogen or removing a hydrogen? Removing a hydrogen. So HNO3 would turn into what? Good. NO3 minus. Make sure you keep track of what's going to change with the charge, because when we're adding or removing a hydrogen that's positively charged, removing it makes your charge go down, adding it makes your charge go up. The conjugate acid of the peroxide ion, O2 minus, or O2 the 2 minus, what would be the conjugate acid of that? H2O? HO. Remember, only add one hydrogen at a time. So HO, more commonly written as OH, with what charge? Good, just 1 minus. We've added 1 hydrogen plus, so that made the charge go up by 1 charge unit. The conjugate base of HSO4. So if I'm looking for a conjugate base, am I adding a hydrogen or removing a hydrogen? Removing one. So what am I left with? Sulfate. Good. SO4, 2 minus. The conjugate acid of HCO3, that's the bicarbonate ion. Good. Good. Adding a hydrogen, so it's H2CO3. And what is that? What do we call that? What's the name of that? CO3 is the what ion? Carbonate ion. So how do we name the ion, the acid made from a carbonate ion? Carbonic acid. Good. 8 ions become ic acid, so this is carbonic acid. Any questions about that? Not so bad so far. All right. So do we feel like we could look at an equation and identify what's the acid and the base? Good about that? All right, move on to the next section. All right, so water is special. In chapter 4, when we are looking at acids and bases, and we had water reacting with an acid and water acting as a base, we said that water was amphoteric, meaning it could act as both an acid or a base. So that's why it's so special. Also, majority of the acid-base reactions we deal with take place in aqueous solution. So amphoteric, just like Amphibious means you can be in both land or water. Ambidextrous means you can do what or what? Use both hands, right, with both left or right hand. Amphoteric means you can both donate or accept a proton. Now, water is not the only thing that can do this. As we saw, ammonia and a few other things could also do this, but water is the most common one we see doing this. Because water can act as both an acid and a base, it can actually react with itself, where two water molecules react, one acting as the acid and one acting as the base. This is called autoionization. What does auto mean? What does the prefix auto mean? Yeah, what does it mean? What does auto mean? By itself. Good, by itself. So autoionization means it ionizes itself. So ionization, we saw in chapter 4, was when an acid or a base, something that was molecular, went into water and became an ion. It became charged. Autoionization means that it can charge itself or react with itself. So this is what it looks like. We have two water molecules. One of them is going to act as our acid, one's going to act as our base. So the one that's acting as an acid is going to donate its proton. The one acting as a base will accept its proton. So the one acting, let me do that backwards compared to what they had. Actually, they have it backwards. Yeah, the acid is going to donate it, turn it into the base. So the acid is going to turn to the conjugate base here. And the base is going to turn to a conjugate acid. So it's not one molecule of water is both an acid or base. It's one molecule of water acts as the acid, one molecule of water acts as the base. And the products are both hydronium and hydroxide. And here we have two molecules of water produce one of each, one molecule of hydronium, one molecule of hydroxide. Now we have reaction arrows that go both ways. What does that mean, that the reaction arrows go both ways? The reaction is reversible, which means that it's going to reach a state of what? Equilibrium. Good. So if it can reach a state of equilibrium, then we can write an equilibrium expression for this. So the equilibrium expression, we'll just write K right now. What would that equilibrium expression be for that? What's going to go on the top for this reaction? Is it reactants on top or products on top? Products on top. Good. So what goes on top? H3O plus and OH minus. What goes on the bottom? Nope. Nope. Nothing. Why? It's a liquid. Good. Liquids don't belong in equilibrium expressions, so there's nothing on the bottom. So our equilibrium expression here is just going to be the hydronium times the hydroxide. So hydronium times the hydroxide is equal to our K. Now, in chapter 15, we had Kc standing for concentration. We had Kp standing for pressure. Here we're going to put Kw, which W stands for, what do you think we're dealing with here? Water, right? Just water. So that W is just standing for water. So this is the K of water, the equilibrium of water. Now the equilibrium of water at room temperature, 25 degrees Celsius, is equal to 1.0 times 10 to the negative 14, which, because both hydronium and hydroxide are 1 to 1, if we were to do an ice table, they would both be x, or x squared. So if x squared is equal to 1.0 times 10 to the negative 14, then what is x equal to? Square root of that. So square root's the same thing as the 1/2 power, right? So power to a power, what do we do? Multiply. So what's negative 14 times 1/2? Negative 7. Good. So we get that both the hydronium and the hydroxide have a concentration of 1 times 10 to the negative 7th molar of pure water at room temperature, 25 degrees Celsius. Now, for those of you who've ever had a chemistry class before, the numbers 14 and 7 should stand out as important when you're talking about acids and bases. Why? What? Good. pH scale. pH scale goes from what to what? 0 to 14. And what's so important about 7? Neutral, which is pure water, should be neutral at room temperature. So what we're leading into here is how equilibrium leads into the pH scale. So hydronium is acidic, H3O+. So if the hydronium is the larger component, then you've got an acidic solution. If the hydroxide is what you get from a base, hydroxide is the larger component, you're a base. If you have equal concentrations of both acid and base, as we just saw, then you'll end up with a neutral solution. So from now on, we're just going to deal with acids and bases in terms of in water so that we can use the equilibrium of water to determine whether or not we're going to be acidic or basic. In using that equilibrium expression, if we have the concentration of one, we can very easily find the concentration of the other. Again, using our equilibrium expression, Kw is equal to the product of the hydroxide and hydronium. Doesn't really matter which one you write first. And at 25 degrees Celsius, that's 1 times 10 to the negative 14. So if I give you one, you can solve for the other. Let's try that out. The concentration of hydronium ions in stomach acid is 0.10 molar. Calculate what the concentration of hydroxide ions is in that stomach acid. So I'm giving you that hydronium is 0.10 molar. And I'm asking what is the concentration of the hydroxide ions at 25 degrees Celsius. I'm not quite sure why your stomach acid would be only 25 degrees Celsius, but we're just using that because we know what the equilibrium constant is for water at that temperature. So we're going to take our equilibrium expression, solve for the unknown variable. So our unknown here is hydroxide. So hydroxide is equal to Kw divided by hydronium. Kw at 25 degrees Celsius is 1 times 10 to the negative 14. And our stomach acid has a hydronium ion concentration of 0.1 molar. So what is the resulting concentration of hydroxide? Good, 10 to the negative 13. So dividing by 0.1, which is 10 to the negative 1, power divided by a power you subtract, negative 14 minus negative 1 is negative 13, or you can plug in your calculator if you don't like to do the exponents in your head. Just if you do it in a calculator, just make sure if the bottom has a power, you put that in parentheses. Any questions about section 2, the acid-base properties of water? All right. Already on to section 3, pH scale. So how do we find pH? Our formula for pH is that pH is equal to the negative log of hydronium, which in water, hydronium and hydrogen ion are the same thing. So that's why it says you could write it as pH is equal to negative log of hydronium, or pH is equal to negative log of hydrogen. Doesn't really matter. In water, they're the same thing. Because if you put hydrogen plus into water, you get hydronium. So it's the same thing. So in pure water, we found that the hydronium ion and hydroxide ion concentration were both equal to 1 times 10 to the negative 7th. If you take the negative log of 1 times 10 to the negative 7th, you get the answer 7. which is the pH of pure water at room temperature. So you don't really need to understand logarithms if you don't want to. For this class, you can just, as long as you can find the log button on your calculator, log log, not ln natural log, you'll be fine. A bit of a word about significant figures here. So back in chapter 1, we learned the rules of rounding. There were different rules for rounding whether or not your arithmetic operation was addition, subtraction. We did rounding by the number of decimal places. Or if it was multiplication, division, we rounded by the number of significant figures. Logarithms are neither addition, subtraction, nor multiplication, division, so it has a different set of rules that was not covered in chapter 1 because I knew we weren't going to be doing logs back in Chem 151. So here's what the rule is. For logarithms, the number of significant figures inside of the log is equal to the number of decimal places after the log. So the number of sig figs inside the log is equal to the number of decimal places outside the log. Which if you're doing this in reverse, given the pH, find the concentration, you're going to look at the number of decimal places for concentration to figure out how many significant figures are going to be in your concentration. Number of decimal places in your pH to find what is the number of significant figures in your concentration. For most of these, you're going to have a concentration that has 2 significant figures, so you'll have a pH that has 2 decimal places. 2 places after the decimal. You'll also notice, especially for those of you who are more familiar with trigonometry and logarithms, that if your base is 1, then the power is equal to your log, if the base is 1. If it's not, just use your calculator. It's here. So again, we talked about last time that if the hydronium ion is the larger component, then you're acidic. If the hydroxide is the larger component, you are basic. So therefore, if your hydronium ion becomes larger than 1.0 times 10 to the negative 7, you're going to end up with the pH going down. So you have a pH lower than 7. So acids have a pH lower than 7. Whereas if your hydronium ion becomes smaller than 1.0 times 10 to the negative 7, so the equilibrium shifts to the direction of the hydroxide ion, then you're going to end up with a pH that is greater than 7. So basic solutions have a pH greater than 7. So this table is on page 724 if you're following along. So just the power, with a base of 1, the power, how it affects your pH. Again, if your base is 1, then the power is going to be equal to what the logarithm gives you. So log of 10 to the negative 1 has a pH of 1. That's pretty acidic. Anything larger than 7 is going to become basic. This is on page 724. So some common substances and their pHs. Stomach acid has a pH of about 1.5, so that's very, very acidic. That's pretty far down in the pH range. Lemon juice about 2.0, vinegar about 3.0, grapefruit juice, orange juice. Now urine, you'll notice, varies from acidic to slightly basic. Why might a body fluid like urine have such a big variance? Good, depends on what you eat. If you've been drinking a lot of grapefruit juice, you're probably going to have rather acidic urine. If you've been eating a lot of foods that are very high alkalinity, then you're more likely to have your urine be more basic. On the other hand, here's another body fluid here, blood, slightly basic, but much narrower range. If what we eat can affect our pH of our body fluids, why do you think blood does not vary as wildly as your urine does? Anybody know? not filters, but taken biology. When you have blood is full of cells, and your cells are full of biochemical reactions going on, you've got proteins and enzymes and all that kind of stuff. Enzymes are usually very, very sensitive to pH. If you change the pH, what happens to the functionality of the enzyme? Stops working. Do we want our enzymes in our bloodstream to stop working? No. So your blood works very hard to maintain a very narrow range of pH so that the enzymes all keep on working. If your blood changes its pH outside of that range, then it becomes very, very dangerous, and your enzymes stop working, and it doesn't, take very much to kill you once that point. And the way your blood does that is through buffers, which we'll talk about in the next chapter. Saliva is slightly acidic. Milk is slightly acidic. Milk of magnesia and ammonia are household items you can find that are slightly basic. Rainwater in clean air is slightly acidic. In not clean air, it's even more acidic than this, and we get acid rain. So if I reverse that pH formula here, the inverse of log is 10 to the power. So the inverse of our equation is that we can find the concentration of hydronium is equal to 10 to the negative pH. So we just took our equation, pH is equal to negative log of hydronium, and we inversed it. So take the negative over to the other side, 10 to the power, 10 to the power, get rid of the log. And that's where that equation came from. Both of these equations are on the page 724, 725 spread to go in and out of pH. So let's try this out. Determine the pH of a solution at 25 degrees Celsius in which the hydronium ion concentration is the following. So we have 3.5 times 10 to the negative 4th, 1.7 times 10 to the negative 7th, and 8.8 times 10 to the negative 11 molar. So you're just going to find the pH by the negative log of these things. And none of these have a base of 1, so you're probably going to want to use your calculator for this one. Remember, in neutral water, hydronium ion concentration is 1 times 10 to the negative 7th. So if your concentration gets bigger than that, you should become more acidic, and your pH should go which direction, up or down? Down. So it should be less than 7. So those first two both have concentrations greater than 1 times 10 to the negative 7th, so both of them should have acidic pHs or pHs less than 7. So what's the pH of that very first one there? Good. 3.46. Again, the number of significant figures inside of the log will be equal to the number of decimal places outside of the log. What about that second one, 1.7 times 10 to the negative 7th? Good. 6.77, so slightly acidic. This last one, 10 to the negative 11, is smaller than 10 to the negative 7th, so that one's going to be what, acidic or basic? Basic, so pH greater than 7. And what do we get for that one? Good. Pretty easy so far. We could reverse that, and it's just going to be 10 to the negative pH. Now, because we're reversing it, the number of decimal places and the number that goes into our power is equal to the number of significant figures we get out of it. In this example, 16.5 is on page 726. Any questions about any of those? So what if instead of giving you the hydronium ion concentration, I give you the hydroxide ion concentration? Now you can do what we did in the last section and convert hydroxide ion concentration to hydronium using the equilibrium constant for water, 1 times 10 to the negative 14, and then proceed with the normal pH equation. That's perfectly fine. Another option is to go through a concept called pOH. So if pH is the negative log of hydrogen, then pOH is the negative log of hydroxide. And likewise, we could inverse that equation and find the concentration of hydroxide is equal to 10 to the negative pOH. So these are both on page 726. So how would finding the pOH help us find the pH? Well, just like hydroxide times hydronium has to multiply out to 1 times 10 to the negative 14 for room temperature water, pH plus pOH have to add up to 14. So if I know what pOH is, I can just subtract it from 14 to find what our pH is. And that's probably a little bit easier than converting our concentration of hydroxide to hydronium and then plugging in the pH equation. But again, both are perfectly valid, both work. This is just a little bit shorter. So because the pOH scale, pOH is basically the inverse of pH, its scale is going to be opposite. Things that have a pOH that are smaller than 7 are going to be basic. Things that have a pOH greater than 7 are going to be acidic. We almost never report things in the pOH scale because it is confusing, because it is the opposite. Usually we're just going to use pOH just to find the pH for this class. So let's try this out. Determine the pOH of a solution at 25 degrees Celsius in which the following hydroxide ion concentrations. So same way as pH, it's the negative log of these, negative log of this 3.7 times 10 to the negative 5. Would give us a pOH of 4.43. So that's our pOH. So if our pOH is 4.43, then what would be our pH? How will we find the pH from the pOH? Good, subtract from 14. So 14 minus 4.43 is good. And you could try the other ones on your own, but I think that one's not so bad. So I could ask you for the pH, I could ask you the pOH. And just like with the pH, I could also give you the pOH and ask you to find what the concentration of the hydroxide is. So, any questions about the pH scale or pOH? I feel like we're moving through this pretty quickly, but again, these sections are pretty short. Can you move on to section 4? All right. Strong acids versus strong bases. So back in chapter 4, how did you know if an acid was a strong acid? How did you know? Table, good. Anybody remember how many strong acids there are? 7, good. So we have a table of 7 strong acids. If it's one of the acids on the table, it's a strong acid. If it's not on the table, it's not a strong acid. But the important thing about those was notice the arrows. All of these arrows go one way. What does that mean? It's not reversible. The reaction happens completely. And these are all of the ionization reactions, where they react with water to make our hydronium, and then our acids turn into its conjugate base. So all of these reactions are ionized completely, or at least to a very close to completion, and are non-reversible. So that's what makes them strong acids, is that their ionizations happen almost to 100%, whereas weak acids only happen to a very small ionization percentage, very, very small. So there's only 7 of them: HCl, HBr, HI, HNO3, HClO3, HClO4, and H2SO4. And again, H2SO4, only the first hydrogen comes off in a strong ionization. The second hydrogen comes off in a weak ionization, as we saw back in chapter 4. So why is this helpful in the pH scale? Well, if this ionization happens completely, then our starting concentration of our strong acid will be equal to the resulting concentration of hydronium, which is then useful in finding what the pH is for everything except for sulfuric acid, because it technically has a second hydrogen ion. We'll talk later about how to handle that one. But for the 6 that are monoprotic, meaning they have just one hydrogen ion to give off, the concentration of hydronium, H3O+, is just going to be your starting concentration of the acid. So very easy to find the pH for strong acids. So the question is, calculate the pH of an aqueous solution at 25 degrees Celsius. That is the following concentrations of strong acids. So 0.035 molar HI. So how will we find the pH of that? 0.035 molar hydroiodic, which is one of the strong acids. Because it's a strong acid, its ionization is complete. So if it's 0.035 molar hydroiodic, that means it's 0.035 molar hydronium, which means the pH is just going to be the negative log of that. So what is the pH of that first one? Go 1.46, which is fairly acidic. And for the other two, same thing. The concentration of the strong acid is equal to the concentration of hydronium, so the pH is just the negative log of that. And just as we can go forwards from the concentration of the strong acid to the base, or sorry, to the pH, we can also go backwards and find out what the concentration of the strong acid was from the pH. Using our inverse the pH equation, the concentration is equal to 10 to the negative pH. And then knowing that the concentration of our strong acid is equal to the concentration of hydronium, once we get that concentration of hydronium. So. And this example is on page 731 if you want to follow along with it, but in the interest of time, I don't think we really need to work through these ones. All right, so how do we feel about strong acids? How to find the pH of strong acids? Easy enough? All right, strong bases. So strong bases in chapter 4, how do we recognize that something was a strong base? NH was how we would recognize molecular bases, which are all weak bases. What would strong bases look like? A metal followed by what polyatomic ion? Hydroxide, good. They were all metal hydroxides, specifically group 1 or 2A metals. So group 1A, the lithium, sodium, potassiums. Group 2A, the magnesium, calcium, etc. So group 1A or 2A metals, because they have a metal, they are what? Molecular or ionic? So for example, sodium hydroxide is a strong base because it is a group 1A metal followed by hydroxide. Is that ionic or molecular? Chapter 2. How do I recognize if a compound is ionic? It contains a what? A metal. So is this ionic? Yes, because it is ionic, what is it going to do in water? Dissociate, good. Ionization is how a molecular compound forms ions by reacting with water. Dissociation is how a soluble ionic compound in water simply breaks apart into its ions. So we get sodium ions and hydroxide ions. These are aqueous. Now, is that dissociation going to go one way, or is it going to be at equilibrium? One way, which means just like with these strong acids, the concentration of the base that goes in will give us the concentration of the hydroxide that goes out. Once we have concentration of hydroxide, we can find POH and then pH. So just like we had a table for the strong acids, we have a table of strong bases, but they're easier to recognize because they all follow the pattern of either being group 1A metal with hydroxide or group 2A metal with hydroxide. The reason why there's not as many group 2A hydroxides is because more of them are not water soluble. For example, magnesium hydroxide or milk of magnesia is not water soluble. That's why if you go to the store and you buy a bottle of milk of magnesia, it looks like a liquid filled with this chalky substance that's just suspended in the solution. That's because milk of magnesia doesn't dissolve in water, so they just suspend it in solution. And this table is on page 731. Notice the stoichiometry. Group 1A, all of these produce one hydroxide. But group 2A hydroxides all produce two hydroxides. That's going to change the resulting concentrations. So back to chapter 2 or chapter 4 and how the concentration is affected by stoichiometry. If, for example, I had 0.10 molar calcium hydroxide, what would be my resulting concentration of hydroxide ion? 0.20, good. Because the stoichiometry is 2 to 1, or twice as many hydroxides for every calcium hydroxide. So don't skip that step. If I give you a group 2A hydroxide, and I give you the concentration, and I'm asking for something like the pH, you need to double the concentration to find the concentration of the hydroxide because it will be 2 to 1 for a group 2A metal. Make sense? All right. Calculate the pOH of the following solutions at 25 degrees Celsius. So 0.013 molar lithium hydroxide. So pOH is the negative log of OH. So what would it be for lithium hydroxide? Good, 1.89. How would barium hydroxide differ? The same concentration, so what's different about it? Would it have the same pOH? Good, because you have to double the concentration of hydroxide. So to find its pOH, it's not the negative log of 0.013, but the negative log of what? Good, 0.026. Which gives us what? Good. Notice doubling the concentration didn't have that huge of an effect on the pH. It's because pH is a log scale, meaning it's powers of 10 scale. So multiplying something by 2 is a significantly smaller change than multiplying something by 10. Each pH unit differs by an order of 10. So doubling it was only 1/5 of the effect of changing it by a power of 10. So that's why it did not have nearly as big of effect on the pOH. Mm-hmm. So I gave you the concentration of the strong base and asked you to find the pOH. What do you think we're going to do next? Reverse it. From the pOH, find the concentration of the strong base. So an aqueous concentration solution of a strong base has a pH of 8.15 at 25 degrees Celsius. Calculate the original concentration of the base in solution if the base is sodium hydroxide versus if the base is barium hydroxide. So first thing, I just go ahead and do negative log of that. Or the inverse of log of 8.15. This is our pH. If I want to find the concentration of OH, it's 10 to the negative what? pOH, and that's pH. So we first have to turn that pH into a pOH. How do we do that? Good. 14 minus the 8.15 gives us a pOH of what? 5.8. Now we can find the hydroxide ion concentration. What do we get is the concentration of hydroxide there? Good. 1.41 times 10 to the negative 6 molar. So if that's the concentration of hydroxide and the solution is sodium hydroxide, what's the concentration of sodium hydroxide? Same thing. Good. It's 1 to 1, so it would be the same thing. 1.41 times 10 to the negative 6 molar. What about if it's barium hydroxide? Half it. Good. Divide it by 2, because we're going backwards now. So half it. 7.06. Where the number of decimal places on the outside of the log is equal to the number of significant figures going in. You're right. That should be only 2. So what's the concentration of the barium hydroxide? if you write out barium hydroxide, it's dissociation, get barium 2 plus and 2 hydroxides. So whatever this number is, to go from hydroxide to barium hydroxide, it would be times barium hydroxide over 2 hydroxides, because it is 2 to 1. So that's why we took the concentration divided by 2. Stoichiometry. So that's how to find the pH of a strong acid or a strong base. Now, weak acids. Weak acids differ from strong acids in that they only ionize partially. We show this by having the reaction arrow go both ways. If the reaction arrow goes both ways, that means instead of going to completion, it goes to what point? Equilibrium. Good. So, how do you find the concentration of things at equilibrium? You just took a test on it. How did you find? Ice tables. Good. So what do you think is coming up? Ice tables. All right. So in order to use an ice table, you need to know what the equilibrium constant is. So in chapter 15, when I was asking you what the concentration of the species were at equilibrium, I always said, okay, I always gave you what the equilibrium constant was. So for the equilibrium constant in terms of concentration, it was Kc. In terms of pressure, it was Kp. For the water, we did Kw. Now for a weak acid, we're going to call that equilibrium ionization constant a Ka. Still calculated the exact same way. Still products over reactants. The same way all of our equilibrium constants are written, is just the A stands for an acid. And we only need these for weak acids because strong acids ionize completely. So we can just use stoichiometry instead of using ice tables. Did you ever think saying just use stoichiometry was the easier of the options? At least the faster of the options. So for any acid, we have some sort of an ion here that's going to be our conjugate base with a hydrogen in front of it. So A is just standing for whatever the acid is. It could be fluoride ion, it could be the acetate ion, it could be hydroxide, it could be water, who knows, whatever it is. Reacts with water and you make hydronium and you make your conjugate base, A minus. So if you write out this in terms of without the water, it's just the hydrogen ion on the acid. So you can write your equilibrium expression as products over reactants, the hydronium ion times the conjugate base divided by the original concentration of your acid, or if you want to leave it as hydrogen plus. Doesn't really matter, again, in water, hydrogen plus and hydronium are the exact same thing. But the important thing is if we find what that concentration is, we can use that to find pH. So we're going to use these equilibrium expressions to find the hydronium ion concentration, which will be used to find the pH. So although these all have lower concentrations than 100%, or lower ionizations than 100%, they're still going to vary in strength. So the higher the K value, the more the reaction is going to go towards completion. So the stronger the reaction is going to occur. So within the group of weak acids, they're going to be stronger if they have larger K values. The higher the K value, the stronger the acid, because the more it's going to go towards the products, the further that reaction is going to go. So here on page 735 is our table of common weak acids and their ionization constants. I would recommend having this page bookmarked so you can refer to it. Again, that's on page 734. 735. Yeah, 735 in this edition. So hydrofluoric, HF. Now this is the acid that back in chapter 4 everybody wanted to call it a strong acid because it looks so darn close to HCl and HI and HBr, and all those are strong acids. HF's in the same family, so why isn't it a strong acid? Well, it's technically a weak acid, but it still has, compared to everything else, at least on this table, a very large ionization constant, meaning it's going to be a relatively strong weak acid compared to these others. It has a Ka of 7.1 times 10 to the negative fourth, compared to everything else on this table is smaller. Now, down here, acetic acid is another common weak acid we're going to see a lot of here. Now, remember I said earlier that in chapter 2 we wrote it in the formula form as the acetate ion with a hydrogen in front, and now we're writing it spread out CH3COOH because that is the way that it is the structural formula. So we have a CH3 here, and then the second carbon is bonded to 2 oxygens, and one of those oxygens has a hydrogen. So that right there is the acidic hydrogen that's going to be lost in an acid-base reaction. And it has a Ka of 1.8 times 10 to the negative fifth. So relatively weak acid there. Hydrocyanic acid and phenol, both even weaker acids. So process to find the pH of a weak acid. First of all, we're going to construct our ice table. The top of the ice table, we need to have a balanced chemical reaction. All of these weak acids are going to have the same type of reaction. I have my acid reacts with water to make hydronium and my conjugate base. They're all going to look like that. Now, in the ice table, why have I just tabbed out the H2O column? It's liquid, good, so it's not going to affect the equilibrium expression. So that's why we're ignoring the H2O column. So let's say, for example, we want to know what is the pH of 0.50 molar HF. So we have our starting concentration of HF, no products. We're going to go down by X amount, plus X, everything's 1 to 1. We end up with X squared on the top and 0.50 minus X on the bottom, set it equal to K. Now at this point, how do you solve for X? We're at this point down here on the bottom of the page. How do you solve for X at this point? What do you need to do? Nobody wants to say it because nobody wants to do it. The quadratic equation, right? Why can't we just take the square root of both sides? Good, that denominator is not a perfect square. I saw a couple of people fell into that on the test. On the test for chapter 15, one of the ice tables ended up being a perfect square, one did not. The one that did not, a few people still fell into the pitfall of trying to just take square root of both sides, and it didn't work out. Because that is not a perfect square, you can't take the square root of both sides, so you need to rearrange it, do the quadratic, and they've already done that for you here. Now, good news. Most of the time, you will not have to do the quadratic for an weak acid ice table. Most of the time, you can get away with assuming it's pretty darn close to the square root. I'll show you that in a second. This is on page 736 if you want to follow along, but it's just the quadratic. So, once you have that X, you've solved for X, you can find the concentration of X is equal to concentration of hydronium, so you can find the pH by just plugging X into your pH equation. So in this case, the quadratic gave them 1.9 times 10 to the negative 2, or 0.019 molar. Plug it in, found the pH. I could have also asked you what was the concentration of your original acid at equilibrium, and that's just your original concentration minus X. All right, what about that assumption? We did touch on this very briefly in chapter 15. If K was extremely small, that means it only ionized a tiny bit, meaning X will be really, really small. If X is really, really small, then adding or subtracting it has a very small, practically negligent effect on your concentration. Multiplying by a really small number does have a big effect, but adding or subtracting a really, really tiny number does not. So in chapter 15, we did have a few that we estimated because X was like 0.0001, and subtracting or adding that was not a big difference. And so we assumed that that denominator was pretty darn close, just the original concentration of our reactant. We're now going to quantify when you are allowed to make that assumption and when you are not. You are allowed to make that assumption when the percent ionization is 5% or less. So in this case, for this reaction that we just did, doing the quadratic, we got our X is 0.019 versus our original concentration of our acid is 0.50. So it ionized 0.019 molar from an original concentration of 0.5. So its percent ionization would be 0.019 molar divided by our original concentration, 0.5, times 100. That gives us a percent ionization of 3.8%, which is less than 5%. Meaning we could have gotten away with, instead of doing the quadratic, assuming that X is very, very small. If we assume that X is very, very small, then let's go back to the original equation here. When we get to this point here, if we assume X is very small, we're going to ignore the minus X in the bottom. So we end up with just X squared on the top and 0.50 on the bottom. We assume that X is so small that we can just ignore it. If we do that, now can we take the square root of both sides? Yes, we can take the square root of both sides. Because now we just have 0.50 on the bottom. We can take the square root of a constant. That's not hard. Just plug in the calculator. So if we take the square root of both sides, we end up with that 7. One times 10 to the negative 4th. Pretty darn close to the original answer. So my recommendation, unless you really feel like doing the quadratic every single time, go ahead and make this assumption and then calculate the percent ionization. If you get a percent ionization 5% or greater, then go back and do the quadratic. But if not, then you can just proceed and find the pH. All right. So we are out of time for today, so we will pick this up tomorrow with actually working out a couple of examples of these weak acids, weak bases.